Hi everyone. We're going to start the keynote of Bhavul Gauri, which is the machine learning engineering at Meta, and he will present us a journey through the NLP history. Thank you very much for being here.
Hello, everyone. How are you guys doing? Good? All right, cool. So first of all, thanks, Bernardo. Thanks to the entire SINFO team for letting me do this, for the opportunity to come here and present about NLP algorithms to all of you. And thanks to everyone who's come here, sit down after having lunch. I understand it's hard. So the entire agenda of my talk is to tell you about various NLP algorithms and how they've evolved from something very classical, something very non-ML of sorts, to something very recent as ChatGPT. Quick show of hands, who all have heard of or used ChatGPT? Awesome. Cool. I know how assignments are being written here now. Who knows about Bag of Words or has heard of it? All right. OK, cool. Cool. That gives me an idea. Cool. So the idea is that this is going to be the agenda. Now, I only have like 30 to 40 minutes, and this could be an entire semester's course. So what I'm going to give you today is enough intuition as to how these algorithms have developed, why they were developed, what's the thinking behind them, and what sort of problems they've solved. But I may not go too much deep into the maths of it. That's going to be difficult within the time constraints. Given that everyone may not have worked with ML, we'll start with something very basic, right? Just to give you a little bit of hint of how ML algorithms work. So some of you would have heard about linear regression. It's one of the most simplest models out there. And I'm going to quickly brush through this aspect of the talk, right? So let's say you have sort of a table, you have some sort of a data, and you're trying to predict heart rate. It's a regression problem. You're predicting a number. What you end up doing is trying to learn a linear regression model where the weights and biases, the W and B that you see in bold, those get learned. How do they get learned? They initially start with random initializations. So the numbers in red are completely random. And then what you end up doing is using this formula. It gives you an output. This is for the first row. Obviously, it's way farther from the actual output, so you get an error. Once you get an error, you utilize that to kind of reduce the weights and the biases, or change and update the weights and biases to make it align better towards the value. So instead of 170K, it should go towards 85. And for that, we usually use backpropagation. And here's a simple GIF that kind of tells you about it, right? So there are all those points, and it'll slowly try to keep updating the weights and biases until your line fits the best, right? That's linear regression. Logistic regression is its counterpart for classification problems, right? Classification is when you're dealing with maybe 2 classes, maybe 5 classes. You're not predicting a heart rate. You're predicting, is this person healthy or not healthy, right? So something more so with it, which is bucketized. To do that, there's something called activation function that you introduce, which squishes down the output so that 170K that we were getting would get squished down between 0 and 1. And that kind of gives you a single value output, right, which can tell if the person's healthy or not. So that's ML in like 3 slides. Generally, you have algorithms that are built on top of this. These were the most basic ones. But the entire idea remains the same. You start with initial random initializations for weights and biases, and you put them in a mathematical formula for the algorithm, and then you get an output. There's an error. You try to reduce that error by using calculus. OK? Now let's move on to the interesting part, right? How do we do machine learning with text, the NLP part? Again, let's look at 2 problems, right? Classification and regression problems. On classification side, now if you wanted to, maybe you want to predict the news, or regression side, maybe you want to predict the rent in Lisbon market, right? So these are descriptions. Now these are relatively real problems. What you need to do is, if you want to apply the same WX plus B formula here, You really can't, because your W and B are going to initialize with numbers, but then X is text. And entire of NLP can be summed up in this one line, I feel. The art of turning text into reasonable numbers or meaningful numbers is the science of NLP, right? Because the bots and the machines are going to talk in numbers only. So that's where our journey begins, right? The first algorithm is count vectorizer, right? This is part of the bag of words approach, which you may or may not have heard of. The idea is very simple. If I go out right now in the streets, get into a school, not even a university, and grab a student and just ask them, hey, I have 2 documents, and you need to figure out if they are similar or not. Or if there are 3 documents, you need to tell me which 2 are similar. The first algorithm that comes naturally to our mind is something very akin to count vectorizer. How it works is you need to just see, are there same words, and are there same occurrence or the frequency of words in the 2 documents? If so, then that means that it is, those documents are identical. That's the algorithm, right? Let's go with an example. Let's say there are 4 headlines that we are dealing with. The first 2 are just talking about the weather, and the other 2 are talking about Dwayne Johnson. I don't know if everyone's familiar. He's also known by The Rock, and the other 2 headlines are talking about the same thing, but in different text words, right? So what you end up doing with count vectorizer is first building a vocabulary, right? So what I've done here is just extracted all the words that are there in all of my text corpus. In this case, my universe of text is just 4 headlines. So I've just collected all the words that appear in there. And this process is called tokenization. It's OK if you don't remember these terms later on after the talk. The idea is to understand how the algorithm is working. Tokenization, there are many different strategies possible. So in the previous one, remaining was a token. Here, we turned it into remain and ##ing. This is a different tokenization scheme. Sometimes these kinds of things help reduce the total vocabulary size and hence the memory of the model. The other thing you can do is just reduce the words to their base words or their root words. This is called stemming often. Again, a way so that if it's remaining in one document, remain in another document, you still feel that they are similar, right? So we could stem the words. The third thing, which is very commonly done, is stop word removal. Stop word are words that do not add a lot of value to your document. So something like propositions like be, these, or in, right? These are not going to define your document. So let's just remove them from the vocabulary. And then what count vectorizer does is just assigns indexes to all of the words in your vocabulary. Once you have assigned index, the algorithm is pretty simple. Let's take headline 4. The last word is Lisbon. Lisbon comes at index number 6. Since Lisbon is occurring only once in the headline, the number changes to 1. So essentially, you're just counting the word and changing its particular index, right? And this is as simple as it can get. And now, because you are representing each headline instead of text with numbers, you can apply the same ML algorithms, logistic regression, linear regressions, neural networks, and such. Let's move on to something slightly better, right? So TF-IDF Vectorizer is a slightly more sophisticated formula that gives low weight to tokens or words that are appearing in all documents. So something like the, which we removed in stop word, but think about if you're looking through the medical journals, diagnosis as a word would be there in all the journals, but diagnosis will not tell you which kind of medical journal this or medical document this is, right? So in this case, diagnosis would not be a stop word, but then you want to remove them still. TF-IDF helps do that. TF-IDF is built up of 2 parts. TF stands for term frequency, IDF stands for inverse document frequency. Long story short, TF is kind of telling you number of times the word appears in the particular document divided by number of words in the document. So for will, it becomes 1/6. There are 6 words in headline 1. And IDF is quite the opposite. It looks at the word with respect to all the documents that you have in your corpus. So in this case, will appears in every single headline, right? So even though it's not a stop word, we end up with IDF equal to 0. TF-IDF is just a multiplication. So what this ends up doing is give us an importance weight of that term. And in this case, that's going to be 0, right? So will does not really matter. And that turns into 0, right? And you use the same formula to get a different set of numbers. In this case, it's not ones or twos or threes. They can be in float numbers or decimal numbers. And these end up reflecting the importance a little better than the previous algorithm. Combined, these two algorithms fall under the category of bag of words. And the biggest problem that I see with these is, like, while these numbers are reflecting their statistics in the documents, they are not really representing the meaning in any way, right? So these numbers do not in any way reflect that, a particular word, let's say green is a color, and green and color should be similar, but then it would not be able to do that right now. So that's where we come to the next algorithm, which is word-to-vec. By the way, I'm going to move quickly through slides because we are all waiting for ChatGPT and how that works. And to get there, I need to go through everything else first and explain to you everything else. So word-to-vec, right? Word-to-vec, or word embeddings, as they're called, is based on this philosophy that you judge the words based on their company. And that really works, just like it works with humans. And to give you an example, right? If you think about these sentences, have a great day ahead, or have an amazing day ahead, or my phone can record in 4K resolution, his phone can shoot in 4K quality, right? I'm changing the words in bold, but they kind of mean similar things, right? So there is this aspect in a language, especially in English at least, so that your words are, similar words will be surrounded by similar neighborhood in sentences. And we try to utilize that occurrence in the English language or in any language for word embeddings, building word embeddings, right? So if you try to think about these examples, and if you try to plot them in a hypothetical two-dimensional curve, right? So you expect that great and amazing should be somewhere near each other, record and should be somewhere near each other. And at this point, these are somewhat more meaningful numbers that are representing them, just because you have a certain aspect of semantic attached to it. Let's say these were the coordinates. Generally, instead of just having 2 dimensions, these are 50-dimensional or 300-dimensional. The reason for that is it's able to encode better meaning or more complex meaning in that case. Just 2 numbers are not able to encode good meanings for all the words in the entire language. But how does this work? How do we get to those numbers, right? How do we get to numbers which are meaningful enough that we can do something like this? That if we get the vector or the numbers that represent king and add to that the vector that represents woman and remove the vector that represents man, then we get a vector that's very similar to queen, right? So this was something that made word embeddings popular, that it was able to do something like this, that the way those numbers were represented, you could do arithmetic between them, and that worked. So how do we get to those numbers which are meaningful, right? So we train a model called skipgram model. There is another approach to this, but I'm going to stick to skipgram for now. And how do we do this? We just pick out data from Wikipedia, data from internet, data from books. You have naturally occurring sentences there, which are legit, and you start working with them in the same way, that you pick up a window. So let's begin with an example of this sentence, right? One should not drink and drive. What we're going to do is we're going to pick up a window of 5 words, right? You could change your window length. And what you're going to do is you're going to do this window spanning across all your sentences, all your data. And what you're going to do for now is just process this one sentence and see how the algorithm works. So for 5-word window, you pick up the center word, and you tell the algorithm that, hey, if this is the input word, then I want the output word should be the neighbor words, right? That's the idea. It might seem unintuitive right now. Keep with me right now, it's fine. As soon as you have something like that, it looks like a ML problem that could be solved, but then it's not the easiest problem from a mathematical perspective, so you turn it into a binary classification problem. So whenever the input and output match, you make them both as inputs and turn the output to 1. And for output to be 0, or for negative examples, you can just randomly pick a word from dictionary, right? There's a good chance that that would not be in neighborhood. So in this case, random and purple, those are the words I picked up. And in this case, now you have a classification data set with you, right? Very similar to the classification data set that we saw at the starting. What you end up doing in this to learn word embeddings is just start with random numbers that represent a word. They will not be meaningful at the start at all. And then for the input and output words, the numbers that you've gotten for them randomly, you try to do a dot product, and then you do a sigmoid of them, which squishes the output between 0 and 1. And if it's matching the target, great. If it's not matching the target, you get an error out of it. So let's say input and output word for drink and drive gives you an output which is 0.2, sigmoid gives 0.55. It's supposed to be 1. It's not 1 right now, so we have an error of 0.45 right now there. So you do that, and you get an error. You keep on back propagating that error and changing these weights. The weights themselves are representing the vectors of words in this case, right? So you keep on changing the randomly initialized weights, and it keeps on updating the vectors that should be representing each of these words. And eventually you end up learning something which gives you that sort of arithmetic nature, that these words have some meaningful semantical nature to them. And there are multiple variations of these. Some work on statistics, some have tweaks which let them work with out-of-vocabulary words that they have never seen in the dictionary. But that's something that you guys can read up on your own as well. One particular thing I wanted to mention was how Spotify used this, right? So they did not do this for NLP, but they turned the same concept to build song embeddings. So when they look at user history of somebody's playlist or somebody's history of what sort of songs they've played, they use that data to turn it into a similar thing, that you have 5 songs, you pick up the middle one, and you try to generate an embedding of that given the context or surrounding songs, right? And this ends up giving you embeddings for songs. So the idea is simple, right? It doesn't have to be limited to words itself. The same concept can be applied. You're judging everything based on its surrounding, and it works. And this is what they were using for a long time for generating those weekly playlists or daily playlists. The challenge with everything that we've talked about so far is that it's still not considering the sequence of things. So let's talk about the third kind of NLP problem, sentiment classification, right? Let's say somebody's writing a review for a movie, and this is what the review says: completely lacking in good acting, good direction, and a good cast. Right? It can happen. English is a funny language. Somebody can write it this way. What's going to happen is that if you're using the word embeddings, we will have embedding for each of these words. We have word embedding for completely, for lacking, for good, for acting, and so on and so forth. And what we generally do for sentences is that we average the embeddings of all of those, and that gives you a single embedding for an entire sentence. Now, if you use that for sentiment classification, there's a good chance that it will mispredict it as positive sentiment, just because there are way too more positive words in the sentence than negative. And what's getting missed out is the order of words, right? Because in word embeddings, when you're averaging, you're not considering the order in any way. But in this case, it's completely lacking, changes the meaning of the entire sentence. So this is where we start thinking about how do we solve this, and this is where we come to something called sequence models, recurrent neural networks, LSTMs. We'll try to talk about them now. And we'll start with something very basic that we started with at the starting of the slide. Logistic regression, y is equal to wx plus b. There's a sigmoid missing there. Forgive me for that. And this is just a neuron, right? A single neuron. If it was a neural network, you'll have a lot of these. What we want to do is, in a recurrent neural network, we're going to just shift the orientation just to make it easier for everyone to understand. And instead of sigmoid, we change it to tan h, right? So the activation function changes. Instead of squishing between 0 to 1, we squish between -1 to 1. And the important aspect or the unique aspect of recurrent neural network is that we're going to pass the context or the output of one word to the next word. So we're going to introduce the order aspect into this. So let's say word 1 was getting inputted into the neuron, getting an output. That output's also going to go into the processing of word number 2, right? And how this is going internally is that we are concatenating the two things. So word embedding for word 2 plus the output of y1 or the first word, those get concatenated, and then you do a tan h. And this is something that you can keep doing on for in the entire length of sequence, and this is how you're kind of adding some sort of a sequential nature. So let's say those were our sentence words, completely lacking in good. They had some random word embeddings. Let's assume that those were meaningful. You pass them on to these recurrent neurons, and they're trying to learn weights and biases of their own, but they're also passing the context forward. So in this case, what's going to happen is when you have the very final output of good acting, let's say, and you pass that to something like logistic regression or a neural network, it's going to be more likely to predict the correct sentiment as negative instead of positive. And the reason for that is you're now passing in the context of completely and lacking till the last cell. There were some problems with RNNs. So for describing problems visually, I've just changed the every neurons to be a different color. What happens here is the problem is called vanishing gradients. So remember when I was talking about learning and updating those weights and biases by backpropagation through calculus? Those backpropagation only last so long. So when you'll start from backpropagating from y5 until it comes to y0, its effect is lost, right? And this can work for a sequence of 5 words, sure, but 50, 500 is not going to remember what was said at the starting. And that kind of defeats the purpose to some extent, that you can't remember what was said at the starting. And that gives rise to the next algorithm, right? Long short-term memory network, LSTMs in short. This is kind of looking the same, and it is in some sense, but it introduces a new arrow in there, right? Cell state or memory state. What it's supposed to do is provide a mechanism for the model to remember things for a longer duration. And how does it do that? If you zoom into one of the neurons, it has a bunch of operations instead of just a single tanh there. Now, for the sake of time, I'm not going too deep into, I'm happy to discuss this after the talk in Q&A session or later outside, but not going too deep into how these work. These are 3 gates which take care of basically understanding what should be forgotten from one word to another, what should be remembered, and how should the output be processed. So when this input is getting processed, how much of this input should I take into account, and how much of previous outputs I need to remember. And it kind of jumbles among them and decides or learns by itself how much it needs to remember and forget. So this is the difference, right? RNNs and LSTMs. And these give rise to sequence models, a whole range of sequence models. And these can be solved for, this was the place where we were able to solve NLP problems in a good way, right? Where ML algorithms started doing almost as good as humans in some sense, but only in a specific category, right? Not altogether a single algorithm doing everything. So if you want to do a sentiment classification, rating prediction, intent classification, you could use a many-to-one sequence model. What's it doing? These green boxes are representing an RNN or LSTM itself, or maybe even a third variant called GRU. But essentially what's happening is you're giving the words, and you're just using the output of the last cell, so last neuron, right? Because it's you only want to predict a single number or a single word out of this, like what was the rating or what was the sentiment. This is called many-to-one because many inputs, single output. One-to-many is opposite. Let's say I give it that generate lyrics. There's an algorithm that I've written which generates lyrics for songs based on their genres. I will give it a genre of pop. That's a single input, but it'll generate lyrics, so it's going to generate many different outputs. Same architecture, just that we are using it differently. Many-to-many is also possible. Let's say you have an entire news headline and you want to extract all the names of companies like Meta, or names of political leaders or actors or any famous entities. Then what you're doing is you're passing in as input the entire sentence, so all different words, and you're getting as outputs for each word whether it represents an entity or not. So again, you're getting same sort of outputs. And you can use that for entity extraction, parts of speech tagging, understanding whether this is a verb, object, noun, so on and so forth. Many-to-many can also come in this form where your input and output length don't match. The single famous thing here is translation. When you're trying to translate from one language to another, the input length may be different than output length. And this general idea of sequence model called seek-to-seek get visualized or sometimes decoded this way, that there's an encoder step which is taking care of all your inputs and forming a representation for them, taking care of the order, and the decoder step is taking care of your outputs, so processing the outputs, making sure the right outputs get produced, right? There's still a problem with this now. So we have now added sequence. We have now made word vectors meaningful. It should work. It does work. You can still do that for all kinds of problems that you have. But the challenge is that if you have a big paragraph, instead of 2 words here, let's say there's a big paragraph of 200 words on the encoder side, right, that you're trying to process. A single vector or a single arrow from encoder to decoder is not going to be enough to share the meaning of entire paragraph for a translation, right? So that becomes a bottleneck. That how do we kind of take care of entire meaning of the encoder into a single thing, right? And for this purpose, I'm going to use this example of translation. So a technical talk, which should translate in Portuguese to uma conversa técnica. Sorry if I butchered that. And let's try to look at it from a translation angle, and that will move us to a newer algorithm and get us closer to ChatGPT. So we're looking at translation, right? So right now, the whole system could be depicted like this. There's a context vector that gets passed from everything in English to everything that's supposed to be in Portuguese, and that is a single vector, single embedding. Now, 1 second. What happened? Sorry for that, guys. Yeah. All right. So let's look at the translation problem, right? Now, one way to kind of deal with this, a simple way is, instead of just using a single vector, let's pass context from each of the input cells and let the decoder take care of it, what it wants, what it doesn't want, right? And that's what people try to do initially. Let's just add outputs of each of them instead of just the last one, and let the decoder take care of what should be the context, how much of it should it use. And for kind of defining how much it should use, we add new weights, alpha 1, alpha 2, alpha 3. And context vector ends up being a weighted sum of those. And alpha 1, alpha 2, alpha 3 are basically numbers between 0 to 1, right? Which are describing that, hey, I want 25% of the output of H1, 25% of H2, and maybe 50% of H3, right? These are called attention weights, and that brings us to attention mechanism. They are not chosen. We can't give them, right? So essentially, these are learned as well. Just like those weights and biases in your original ML models, you end up learning these with your language. So the language automatically figures out, based on that, the translation data sets that you have, that what it should pay attention to and how much. And you do that not just for first input of decoder, but every single input, right? Because every single input would want to pay attention to different words. Conversa would want to pay attention to talk. Uma would want to pay attention to right? So on and so forth. So you end up doing this. And the attention formula can be described in a more general sense like this. They get learned, as I said. And there are many different other ways to define attention. All of them work well, but yeah, it's basically a choice. And this is how it looks, right, for now. Now, another thing that researchers end up doing is to change it to a multi-head attention mechanism. So instead of every single decoder cell paying attention to like building attention weights once for each of them, they will do it multiple times, maybe 3 times, maybe 4 times. Now, why do we want to do this? Let's say there's a riddle. I give you maybe 5 seconds to look at it. I'm the beginning of everything, end of everywhere, beginning of eternity, end of time and space, right? What am I? And I immediately just vanish the riddle. Not every one of you is going to remember the entire riddle, right? Maybe one person's going to remember the first chunk, another person's going to remember the last part, another person might remember the middle of it, right? And together, but to solve the riddle, you need all of those pieces, right? So sometimes, in a similar analogous way, it's useful to have a model be able to attend to different things for the same output, especially in case of translation, where sometimes a single word in a different language could mean multiple words in the input language, right? In which case, it's important that it's able to attend or pay attention to different input words. So the entire diagram, I've just simplified it to say something like simple multi-head attention block now. So every output is going to multi-head attention block. It's going into input of every decoder, right? Makes sense. So far makes sense. And the sole purpose of this was to pass the context in a way that would not reduce the meaning of inputs in any way. Now let's look at another problem. What if our input sentence was not something as simple as that, but it was like this: animal did not cross the street because it was wide. Now in this case, there's another nuance of language that comes up. There are pronouns. What is it referring to? Is it referring to street? Is it referring to animal? In this case, it's referring to street because the word at the end is wide. If I change the word at the end to tired, it will refer to the animal, right? So there's a chance that maybe when words are getting processed only on the encoder side, at the time of it, when it's processing the word it needs to know which word is it trying to process, what should be the meaning of it, right? In which case, there needs to be some attention mechanism within the input layers itself. And they need to pass context information among themselves. And this means that maybe we can have a similar attention mechanism just on the input side, just on the encoder side, right? So we try to do that. Let's add another attention encoder there. So there's no interaction between encoder decoder, just among these three words, right? And I've changed every word, since every word is being passed as an embedding, just to kind of reflect that more visually, I've put it like those colorful boxes. We added a neural network just for the sake that it can learn more. You want to do the same thing on the output side as well, just for similar reasons, right? What if your language, the words that you saw as input right now, where there was an it, that could be on the output side as well. So you end up doing that. You end up adding multi-head attention mechanism on decoder side as well. And now your architecture looks something like this, where you have all of these words going into the attention mechanism, paying attention to each other, and encoder and decoder are paying attention among themselves. You're passing all of that through a neural network further to get to a final output of some sort. One thing that I did not have enough time to explain in this talk are these extra bits that get added. Skip connections and layer normalizations are just there. Think of them as components that can make your model more stable, more resilient. And that's the only reason those have been added, right? But the core aspects was those attention mechanisms. One thing that gets missed as soon as we do all of these changes is that we've forgotten the order again. We were processing in this slide everything parallelly, right? Everything's getting attended to each other, going through the neural network together. There's nobody knows on decoder side was the first word, was technical the second word, was talk the third word or not. So we have forgotten order again, and to add a bit of that order, we add some positional encoding. These are again other vectors which are just trying to represent what was the position of this word in the input and on the output side, right? And this ends up learning positions better and encoding them in the model. And now it's another encoder-decoder architecture, but it looks slightly different, more colorful, maybe more complex when you look at it, but hopefully you can make some sense of this, right? Generally, if you want to learn larger models, larger language models that are becoming the rage right now, you repeat encoder blocks and decoder blocks n times. So you don't have just one, you have multiple layers of this and multiple layers of that as well. So there's a lot of attention, a lot of neural networks in between. And let's see it in action. Let's try to do how translation would work. We have a technical talk. On the decoder side, it will start with some special tokens, start, mask, and mask. When I say mask, the decoder can't see what is the word there, because if it sees that, that'll be cheating, right? When it's trying to train, it should be able to learn that what should point to Uma. This whole thing will go through the block ends up producing probabilities for possible words, and as it learns the weights and biases, it will predict UMA with the highest probability. And then UMA gets into its place. You go on to the next word, it predicts the next word conversa, it predicts the next word mask. This entire architecture that you just witnessed going from sequence model is called transformer, right? And this is the underlying architecture for all your language models right now. All large language models, be it BERT, ChatGPT, GPT-3, whatever else you have heard of. So this is the main crux that I wanted all of you to get some intuition on as to how this is going on. And now let's get into the, before that, there are more specifics around this transformer model on how their attention mechanism is used. As I told, attention formulas could be different. In this case, they use something called scale dot product attention, which could be a half-hour talk in itself. So instead of doing that, I've come up with the recommendation, right? There's a whole playlist on Rasa on YouTube where you can watch them explain this particular formula of attention mechanism if you want to really learn that. Now let's talk about BERT, right? We are heading into the domain of language models now. And we're getting closer and closer to ChatGPT. So without transformer that we just witnessed, which maybe some of you would not know of, but some of you would know of BERT, right? Without transformer, we would not have BERT at all. Why? BERT is just the encoder part of transformer. That's what it is. So its name itself says bidirectional encoder representation from transformer. And the purpose for BERT was that it gives us great word embeddings which are contextual in nature, which have this information of sequence, which works better than RNNs, LSTMs. That's the main advantage of using something like BERT. There were variants of BERT. One is a smaller one is a larger one. Depends on how many encoder blocks you put one on top of another. Let's see how it works, right? How was BERT model trained? We know the architecture now. It's just the encoder part of transformer, right? We completely get rid of the decoder part. But the way it's trained is where uniqueness lies of BERT, right? They came up with something called masked language modeling. The idea is similar to what I showed. There's a mask token. It tries to predict the mask token. And then if you want to utilize BERT for your own domain, let's say you want to do sentiment classification, you will usually do a supervised learning or something called fine-tuning after you use a pre-trained BERT model. But let's talk more about the first part, right? The pre-trained model, right? Because fine-tuning anyone can do by picking up one of these libraries like Hugging Face. On the pre-training part, how it's working is that you have the entire sentence. It will just mask one of the tokens. So in this case, for example, the 5th index gets masked, right? Which is supposed to be improvisation. And the model should be predicting the probability as highest for improvisation. If it doesn't, there's an error, and it tries to learn that. This is called masked language modeling, where it will randomly mask some of the words within the sentence, and the model is assigned the job to predict those correctly. The other task that it's trained upon is called next sentence prediction, where it's trying to just learn if you give it 2 sentences, are they related to one another or not? Is the second sentence supposed to be the next sentence after the first sentence? This gives us a more meta-learning capability of learning about paragraphs rather than just words in their sequence, and making sense of what are related sentences and what are not. What this ended up doing was that these training tasks with the scalable transformer architecture ended up producing state-of-the-art results back in the day on 11 different NLP tasks, right? And this has not happened before until this time, right? So it was named as BERT, being the ImageNet moment of NLP and such, and it kind of sparked this entire generation of large language models. And the other thing was that it was taking both previous and future words into account. So it was looking both ways and just predicting the masking words. Sometimes that's important. There were other uniqueness factors as well, or accessibility, right? They immediately open sourced it in PyTorch and TensorFlow, which made it more accessible. Now let's move on to GPT, right? GPT is also utilizing transformer architecture. It's slightly different than BERT though. BERT was using the encoder side. GPT will use the decoder side, right? We'll start with GPT-2, come to GPT-3, and then go to ChatGPT. So GPT is using just the decoder part, unlike the BERT model that we came across. It's also another large language model that got trained on internet data, books data, all the data that you can find on text online. What were the major differences other than encoder and decoder? The task used is different. So on BERT, you were masking randomly some tokens, looking in the, when I say looking in the past and future of that masked token, I mean that the attention mechanism could see both ways, right? And it was trying to predict the masked token. In this case, it only goes left to right. So it's only trying to predict the next word. It cannot look into the future at all. So that's the difference in the task. These models which only predict the next word are called autoregressive models, and it uses masked self-attention to make sure that everything in the future gets masked and it only sees the past words, right? So that's how it works. Just a small GIF, like for example, you give input one by one and it tries to predict the next output. So it's always just predicting the next word and it's trying to learn that. What's happening in decoder here is that you have this self-attention that I just talked about. Robo must obey orders. So order is the one it will predict based on paying attention to all the previous words. But there's one slight change with the decoder part. You remember there was a multi-head attention layer which was encoder-decoder interaction. We don't need that anymore because we are only dealing with decoders right now. So GPT-2 gets rid of that. And on the decoder side, again, there are multiple blocks. And each decoder block just has a neural network and self-attention mechanism. So a simple architecture like that can scale up, can be parallelized, and can have billions of parameters and end up learning state-of-the-art results and produce text outputs. So at the time, it produced state-of-the-art results just majorly for text generation related tasks and even question answering, which is also a text generation task. It was a much larger scale model, so it had 750 million parameters. When I say parameters, those are the weights and biases that we started with, versus BERT, which was at the time only about 300 million. So the difference, major one, was that BERT gave us pre-trained embeddings with their pre-trained model and told us that, hey, if you want to use it to work on your specific model, just use this pre-trained one, and then pre-trained embeddings will give you enough language information in your words, then add a small network on top, do a fine-tuning for your specific task, it'll work great. And it does to this day. GPT-2 was not built from the same intention. Their intention was, hey, you don't need to fine-tune it, right? This is a huge model. I don't expect that you will be able to fine-tune it. You'll be able to run it for a few epochs, train it a little more. So the idea was that they wanted to build something that could work without fine-tuning and could approach more generality as much as possible. That's what leads us to GPT-3, right? GPT-3, architecture-wise, exactly the same as GPT-2. There's hardly some tweaks on the way they are doing their infra or optimizations, but other than that, nothing else. So it's working in the same way. The only thing that was improved was we went from 800 million parameters to 175 billion parameters. So huge scale change. You fed it more data. The architecture is scalable, the transformer architecture, so it was able to take care of that. And then you end up, predicting the next word. It ends up learning much, much better things. And what this led to, what that scale led to, was something called few-shot learning, becoming more accessible. Few-shot learning in the field of machine learning is when you do not have to fine-tune your model. At the time of the prompt, or at the time of taking an inference from the model, you can give it what you want it to do. So you can ask it, hey, just translate English to Portuguese right now. And you give it a few examples. Hello means hola, and so on and so forth. And you leave the last input, like what does cheese mean? And it'll give you the output, right? So at runtime, it's able to figure out whatever you're asking it to do. Instead of translate, if I had said, do an addition, and I show like 1 plus 2 maps to 3, 3 plus 5 maps to 8, and then I ask it like 55 plus 27, it will be able to give a right output. So there was a little bit of generalizing capability here that emerged from this, right? And that was what made it interesting. matter of fact, so the idea, first of all, was that it performed as well as a fine-tuned BERT model without doing any fine-tuning for a bunch of tasks. And that was the main highlight for this. And it introduced this idea that language models can be general-purpose interface. So you can just talk to them, tell them what you need from them, and they'll answer you in the right way, right? And that kind of emerged from GPT-3. And that brings me to the last part of the talk, ChatGPT, right? Everyone's used it here. I asked it, can you explain what ChatGPT is? But I don't think we need that anymore. Underlying model behind ChatGPT is GPT 3.5, which for all intents and purposes is GPT-3 that we just discussed. So that's sort of a scale. But instead of just text, it has code as well implemented into it. So ChatGPT, for example, can give you code snippets. That's what GPT 3.5 is instead of GPT-3. The interesting part with ChatGPT is, even though the underlying model is GPT-3 or 3.5, we are not giving it few examples to learn anymore, right? I'm directly giving it a prompt, and it's giving me an answer. So what has changed from GPT 3.5 to ChatGPT that it's not required to give it a few examples at all? That brings me to the idea of capability versus alignment. So as a model, it's very capable to understand languages, to understand what's the meaning of different sentences, what's the logic behind things and such. And it's able to memorize everything among all the languages that basically exist in the data set. But it's not well aligned with what we want as human from an output perspective from the model. Because this was trying to predict the next word, right? This is a plausible output. Imagine at some point in the internet, somebody would have an assignment sheet asking that question by question by question. First question, explain how merge sort works. Second question, explain how bubble sort works. The model would have gone through that in its data set while it's training. And it would have learned that, okay, once somebody asks me explain how the merge sort works, maybe the next word to predict is explain, the next word to predict is how, and then so on and so forth. It will give us an output which we don't want, right? But this is a plausible output. It's only happening because you've trained it in such a database. What we want to change here is the output. Output should have been what the merge sort should be, right? And for that, what OpenAI has done on ChatGPT side is achieve this alignment through 3 different steps. The first step is something we have already spoken about, underlying pre-trained GPT model, which is GPT 3.5 or GPT 3, which we spoke about how it's getting trained, next word prediction. We're going to talk about second and the third step, supervised fine-tuning and reinforcement learning from human feedback. Now, one thing that I want to note down here is that all of this is extracted from Instruct GPT. OpenAI never really wrote down a paper on how they have built ChatGPT. What they've said is that it has been trained in the same way as Instruct GPT, which is another one of their models. So they say that it's basically trained in the same way with some optimizations under the hood. So we are going to basically rely on how Instruct GPT works and kind of approximate that to ChatGPT. Underlying pre-trained GPT model we are all aware of now, how GPT-3 is working. Let's go on to the second part, supervised fine-tuning model. Now, because those issues can happen, explain how merge sort to explain how bubble sort, what they ended up doing was they wanted to fine-tune this GPT model. Originally not intended, but at once they can do it, one-time effort. What they did was they made humans act as both the chatbot as well as the human, right? So one human would give input response prompts, the other human would try to be an ideal chatbot that OpenAI wants to publicize. And then they'll try to further tune the GPT-3 model by using this sort of historical conversations where humans have been on the both ends. And that would end up making it better in the sense like it will probably not give explain how merge sort, explain how bubble sort works after explain how merge sort. It will probably give the right answer, right? So it ends up pushing the model in a direction where it gives more aligned responses to humans. The challenge with this is, however, that this is very expensive, right? You need humans who are sitting there and trying to write both prompts, and then another human is trying to answer them in the best way possible. So this is not scalable at all. They can't do this for all languages, for everything, and sit down and prepare this data set for years and years and years, right? So we wanted to get better than this, and that's where the third part comes up, reinforcement learning from human feedback. So they did do that with a smaller data set. We don't know the size or the scale of that data set, but it was small. And what they scaled up was the third part of it, reinforcement learning from human feedback. Now, reinforcement learning, for anyone who's not aware, in a TLDR version of that is that it's very similar to how humans learn. You basically build an environment, you build an agent, and you build an actions that it can take, and based on actions, environment changes and it tries to learn. There's a reward model. A simple example, Mario game or any other games that you can think of, Atari games, you have a player, you can move. Every move gives you some points or some rewards, and those rewards lead you to winning, and the model keeps on learning by just taking random steps. What you want to do here with reinforcement learning is they try to create a labeled data set of conversations by just passing it through model. So the existing model that we got from step 2, supervised fine-tuned model, you give it a bunch of prompts, it will give you a bunch of responses. Instead of one response, they internally took 8 or 9 responses, different responses from the model, and then humans just did the work of ranking them. So if you had 5 different responses, A, B, C, D, and E from the bot, they decided what is the most aligned response to what humans want, right? And most preferred to least preferred responses from the bot. And then they ended up building a separate model. So again, kind of utilizing the word embedding technique, skipgram technique, turning that into a binary classification problem, which itself becomes a small model of its own, which is called the reward model here. So for reinforcement learning, you need a way to pass on the rewards. And in this case, then the multiple outputs that the model with ChatGPT would produce, it will get passed through the reward model. It will generate some scores for these reward models. And this is trained on the human labeled data set. Ranking responses is much easier of a task than actually writing the responses. So this kind of works. So finally, this is how ChatGPT kind of looks like. The policy model that you see is basically the GPT 3.5 model. You give it some prompt, it will take an action and generate a response. That response changes the state in the sense of the history of the conversation. Once it changes the state, there's a reward model that kicks in, which produces that, okay, there were all these responses. Which one have I ranked higher? Which one have I ranked lower? If it doesn't meet human-aligned responses, there are weights in there that get learned in a reinforcement learning setting. And it keeps on iterating to make the ChatGPT get more aligned with human responses compared to a more vanilla GPT-3. And that's for reinforcement learning is using something called proximal policy optimization, which is basically ultimately using neural networks inside and slowly tweaking the weights, but essentially doing the same thing just in a more reinforcement learning method. We don't have enough time to kind of go through enough on PPO, but yeah, that's where my talk kind of ends. All these slides are available on this URL. It's shared on my drive, so you can access it, use it. Feel free to use it anywhere else as well. And if you want to connect with me, those are my social credentials. Yeah, that's all, guys. Thanks a lot for listening.